Hi, welcome to Science with Mrs. Stone from Advancing Science at Gettysburg College. Today we are going to investigate seafloor spreading, look for evidence of seafloor spreading in our models using a Vernier LabQuest and a magnetic field sensor. Before we get started with our experiment today, let's take a little bit of time to think about the different types of plate boundaries and how the plates move relative to one another at each of these different types of plate boundaries. So go ahead and pause this video for a few minutes and think about the answers to those questions. Are you ready to check your work? There are three different types of plate boundaries. The first is called a transform, and we see that in the upper part of our image here. That's when two plates slide past each other. That's where we usually see earthquakes occurring, is along transform plate boundaries. The second type of plate boundary is a divergent plate boundary, which you see right here in the center image. And that's where two plates are moving away from each other. And the third type of plate boundary is the convergent plate boundary, and that's shown in the third image right here. And that's where the plates are moving toward each other. Often you end up with subduction zones here if we're thinking about a continental plate and oceanic plate meeting. The oceanic plate is more dense, and so it will get pushed under the continental plate, causing a subduction zone along here. Now, for today's lesson, we're going to be focusing on mid-ocean ridges and seafloor spreading that occurs at those mid-ocean ridges. And those occur along divergent boundaries. If we look here at our graphic and we look at the center of the ocean here, we can see an ocean spreading ridge. There's one of these that runs through the center of the Atlantic Ocean. And we can see in our graphic that there are two plates, and based upon the direction of those arrows, we can tell that those two plates are moving away from each other. So we have a divergent boundary. And seafloor spreading occurs at these mid-ocean ridges where the divergent boundary is causing the plates to move away from each other. And that causes the seafloor to spread. As these plates are moving apart, new material from the mantle is coming up through the opening in between those two plates, and it cools, hardens, and then pushes the old seafloor out to the edges. Now, Earth has a magnetic field. And as you can see in the picture here, the magnetic field sort of looks like a force field around the Earth, and it protects the Earth sort of like a force field. It helps to deflect solar winds and some radiation coming from the sun. The Earth's magnetic field is what makes compasses point north. Now, when seafloor spreading is occurring and we have new ocean floor material coming up, that new molten material coming up through our divergent plate boundaries, that molten material has iron in it, and iron is magnetic. And so those iron pieces in that molten material are sort of flowing freely because they haven't solidified yet. And those iron pieces in the molten material will actually align themselves, sort of like a little mini magnet in the seafloor as they start to cool down. So those little bits of iron in there, they have sort of a north end and a south end, and they'll align themselves up with the Earth's magnetic field, so the north is pointing north and the south is pointing south. And then as that new seafloor material cools and hardens, those iron bits get locked into that position as little mini magnets with north pointing north and south pointing south. And so what we're going to do in our lab activity here in just a few minutes is we will use Vernier LabQuest devices and some small seafloor spreading models, and we are going to measure how the magnetic field is across that model. So we'll go ahead and continue on here and get set up with our experiment. To conduct our seafloor spreading lab, we'll need a LabQuest, a magnetic field sensor, and Advancing Science has two different types. One has a clear sensor and the other is this black sensor. You'll also need a seafloor model and a ruler. Step number one on our lab procedure is to get our sensors plugged into our LabQuest. If you look at the LabQuest along the side, there's three ports where you can plug the sensors into. We want to plug into channel 1. It's listed as CH1. Now, if you're using one of the black sensors, you can just plug right into that. If you're using one of the clear sensors, then you'll need to add this gray adapter to the end of your plug so that it can attach to the LabQuest. But then either way, go ahead and take your plug and connect it into the channel 1 on the side of the LabQuest. If the LabQuest is not already turned on, please do that now. The power button's right up here at the top. And you'll also find a stylus on the back side that you can use on the touch screen. Our next step is to make sure that our sensor is being properly identified. If you're using one of the black sensors, once your LabQuest is powered on, you should see on the main screen a red box that has the live magnetic field reading. If you're using one of the older clear sensors, it doesn't automatically identify what kind of sensor you've attached to it. So we need to go through a couple of extra steps if you are using one of the clear sensors. On the LabQuest in the upper left corner, you'll see a few menu options. Tap the Sensors menu, then choose Sensor Setup, and it'll take you to a new screen. Across the top, it'll say CH1 for channel 1, and you want to tap where it says No Sensor so that you can tell it what kind of sensor you have plugged into channel 1. I'm tapping where it says No Sensor. Scroll down in the alphabetical list to find Magnetic Field. Tap Magnetic Field, and then you'll want to choose Magnetic Field 0.3 MT, which stands for millitesla. That's the unit that we'll be using to collect our magnetic field data today. Click the OK button, click the OK button again, and then it should take you back to that main screen. You should see a red box with the live magnetic field reading. Our next step is to zero our sensors, clear out any old data that may be in them. To do that, you'll want to hold your sensor up and away from any magnetic field sources that may be on your desktop. And on your LabQuest screen, find the Sensors menu in the upper left-hand corner. Tap that. Down towards the bottom, you'll see the word 0. Click the word 0. Then you'll see Channel 1 Magnetic Field. Click that, and it should reset your sensor back to about 0. That number may fluctuate a little bit, but that's okay. Our next step is to prepare our LabQuest for data collection. If you look on the right-hand side of your LabQuest, you'll see in the upper right corner it says Mode. Currently, it probably says Time-Based. You want to go ahead and tap on that. It'll take you to a new screen. There's a couple of fields here that you can change. Up at the top where it says Time-Based Mode, you want to change that to Events with Entry. And then you will see two blanks that can be filled in. One says Name. Tap in the Name box. It'll pop up a keyboard for you, and you want to type the word Magnetic Field. And you can hit Done. It'll bring you back to your Events with Entry screen. And now in the Units field, we want to tap in there, and we're going to put our units of millitesla. That's going to be a lowercase m and a capital T. And then hit Done again, and then OK. And it should take you back to the main screen. Now we need to prepare our model for data collection. If we take our look at our seafloor model, in the bottom we have some rocks in here, and then there's actually a layer of magnets that we've placed in here underneath this kind of sand top. There is in our kit a demo model of what this looks like, and it doesn't have this top layer on. So you can ask your teacher to take a look at that demo model so that you can see how the magnets are glued in underneath this top layer. You can see there's a ridge running down the center. This is meant to be our mid-ocean ridge. Around the edges, the plastic edges of your model here, you should see the words north, south, east, and west. Find where it says north and make sure that that is facing away from your body during data collection. On your LabQuest, in the lower left corner, you'll see a green play button. Go ahead and tap that. And that will automatically take us over to a graph screen. If we take a minute to look at how our graph is laid out, look at the X and Y axis. What is the label on the y-axis? What's the label on the x-axis? Now, to collect data, if you're using one of the clear sensors, there's a white dot on the bottom of it. And the white dot, you want to have that facing your model as you are collecting your data. If you're using one of the black sensors, the white dot is on the end, and this end can bend. So I would bend it down at a 90-degree angle like that, and then as you make your measurements on the seafloor model, you will have that white dot pointed towards your model. So either way, you want to make sure the white dot is pointed toward the model as you're taking your measurements. Take your ruler and find the centimeter side of your ruler. Line up the 0 centimeter mark at the far left side of your model and have it run across the center of your model. You're going to leave the ruler in place throughout our data collection today, because what we're going to be doing is measuring the magnetic field every 1 centimeter across our model. So we're going to use that ruler to know the exact position where we should take our measurements. Take your magnetic field sensor, make sure the white dot is pointing down towards your model, hold it over your model, pretty close to your model, and take a look at your computer screen. On the far right side, you should see in red text magnetic field, and there will be a number that's moving around just a little bit. You want to take a look at that, wait for it to stabilize. Now, when I say stabilize, it's not going to stop at exactly one number. It's going to continue to fluctuate a little bit, but you want it to be pretty stable. Once it's pretty stable, then you can go ahead and click the Keep button in the lower left corner, and it will pop up a box for you. It says Enter Value for Event. What we want to enter here is our distance. So our distance from the ruler is at the 0 centimeter mark. So I'm going to put in 0 and then hit OK. Now I move my magnetic field sensor to the 1 centimeter mark. Again, making sure that that white dot is pointing down towards my model at all times. I'm taking a look at my magnetic field sensor reading on the far right side of my screen and waiting for it to stabilize a little bit. Once it's stabilized, I'll click that Keep button again, and now this time I'll type in 1 because I'm measuring at the 1 centimeter mark. Continue on in this fashion until you get across to the 15 centimeter mark on the opposite side of your model. Your graph will look like a series of scattered dots after you've collected all of your data points. In order to connect the dots so that your graph looks like mine, you'll want to, from the graph screen on your LabQuest, click on the graph menu and then choose Graph Options. You'll get a pop-up box that looks like this. You'll want to check the Connect Points box and then hit OK. When you return back to your graph screen, you'll then see a connected series of dots. It should look like a squiggly line, sort of like a mountain ridge. If yours doesn't look like this, if maybe some of your lines are crossing each other, you may have entered in some of your measurements incorrectly. So if your graph doesn't look like this, take a look at the data table that contains the data that is generating your graph. If you look in the upper right-hand corner of the LabQuest menu, you'll see a Data Table tab. It has an X and a Y at the top. Click on that, and when you look at the data that is in your data table there, if you look at the numbers, do you have 0, then 1, 2, 3, 4, 5, and do those measurements go in order? Maybe there's an error in there somewhere. So you can go ahead down and double check your 0 through 15 values and make sure those are entered correctly. If they're not, you can just use the stylus to tap right on the incorrect entry. It'll pop up a keyboard and you can fix that up. It will then automatically fix up your graph, so then you can click back on the Graph tab across the top of the LabQuest, and hopefully then you'll have a graph that looks just like this one. Now that you've had a chance to finish your data collection, it's time to draw your graph onto a piece of paper so that we can do some more analysis on this graph. To replicate your graph on a piece of paper, start by drawing your X and Y axis. Start by drawing these two lines here. Go ahead and use a ruler so that you can make yours look nicer than mine. Once you have your X and Y axis in place, then make sure you include the labels. Magnetic field in millitesla is being measured along our y-axis, and distance in centimeters is being labeled across our x-axis. Next, divide up your y-axis to mark the tick marks for milliteslas. Notice that we are starting in the negative and that the 0 is actually at the middle point of our graph. So a little bit different than some of the graphs that you may have seen before. Along the x-axis here, you want to go ahead and divide that up into tick marks based upon your centimeters measurement. So if you notice here, I've got the 5 centimeter mark, the 10 centimeter mark, and the 15 centimeter mark label. Once you have set up your graph, the next thing you want to do is go ahead and look at your LabQuest screen and replicate the line that you see, that red line that you created as you were collecting your data. As you're drawing that line, try to make sure that you have it crossing the 0 mark. Again, remember that our 0 mark is in the center here of our y-axis. Try to make sure that your line is crossing that 0 mark in the same way that it is on your Vernier LabQuest. So you want to do your best to replicate that exact same pattern that you see on your Vernier LabQuest. Now that your graph is complete, we need to add a few more details to it. So we want to mark the center of our model to represent where the mid-ocean ridge was located. And so that's going to be at the 7.5 centimeter mark because our model was 15 centimeters long. So I'm going to find the 7.5 centimeter mark here looking along my x-axis, and then you should go ahead and lay your ruler right along that 7.5 centimeter mark and draw a line. You can use a ruler so your line will be nice and straight. Then go ahead and label that line that you drew as the mid-ocean ridge. Our next step is to indicate which direction these plates are moving. So let's recall. We have 3 different types of plate boundaries. What kind of plate boundary do we have at mid-ocean ridges? And how are those plates moving relative to each other? We have divergent plate boundaries found at mid-ocean ridges, and we can draw 2 arrows pointed away from each other to represent that these plates are moving away from each other. If you recall back to the beginning of our lesson today, we mentioned that the Earth has a magnetic field. That magnetic field is what causes the iron in the molten new seafloor material to align itself up with the poles of the magnetic field of the Earth. And so in a normal polarity, which you see right here, north is north, so our magnetic north is north, and our magnetic south is south. However, every about 250,000 years, that polarity reverses, and the magnetic south pole is up here, and the magnetic north pole is down here. And that record of the magnetic poles reversing is recorded in our seafloor. Again, because the iron that's in the molten seafloor material aligns itself with the magnetic poles. And so we're able to see when those magnetic poles flipped based upon the pattern that we see in the rocks. Now our next step is to mark our magnetic field reversal. So I'm going to get a different color pen. I'm going to use green to mark my magnetic field reversals. I know when the field was reversed because our line goes either above or below this 0 mark. So each time our red line crosses that 0 mark, we are going to mark that as a magnetic field reversal. So again, take your ruler, lay it along, going vertically to match up with where that red line crosses the 0 mark, and then draw a line going straight down just like that. And you're going to repeat that each time your red line crosses the 0 mark. There we go. Go ahead and pause the video if you have not finished drawing your magnetic reversal lines. Once your magnetic reversal lines are in place, we want to sort of shade this a little bit so that we can tell the difference between a normal and a reversed magnetic field. So I'm going to say that when I see the red line up in the positive area of my graph, that's going to represent a normal magnetic field. And when I look at the area below the zero line, that's going to be a reversed magnetic field. So I'm going to go ahead and shade in the sections of my graph that show a reversed magnetic field. So if I look in this first section right here, my red line is under the zero mark. So this first section of my graph represents a reversed magnetic field. So if you have a pencil, you can just sort of lightly shade it gray along here. If you have a highlighter, that might work too. You could fill in all this area. I'm just kind of being messy and scribbling it in, but you can fill yours in more neatly there to show that this section is a reversed magnetic field. And I'll go ahead and put an R up at the top of that so that I know that that's reversed. My next section of the graph shows an area that is above the zero mark. So that's positive. So we're going to call that normal. So we'll put an N right up top here. And then we'll carry on in that same fashion, continuing to work our way across the graph. When I come to this next section, I see that it's below the zero mark. So this is going to be another reversed magnetic field, and I will shade that in. So go ahead and pause the video and finish marking your graph to show the reversed and normal magnetic fields. Now that you've had a chance to mark the magnetic field reversals on your graph, we'll take a look at it to see if we can notice some patterns and analyze our data. I'm going to go ahead and move to a little bit of a neater version of my graph so that it'll make it a little bit easier for us to talk about. So when we take a look at our graph, the first thing we want to notice is what patterns do we see? Hopefully you notice that there are alternating patterns in the normal versus reversed magnetic field. Now let's take a look. Start here in the center, the mid-ocean ridge. That's where the action's happening. Remember, that's where that molten material is coming up in between those two plates and pushing them apart. And so this is where we're starting. We've got these arrows moving us away from this direction. So if we start our eyes in the very center of the graph and then work our way out towards either side, what do we notice? Hopefully you'll notice that the pattern is the same on both sides. If we start here in the center at our mid-ocean ridge and we look to our left, we see normal magnetic field, and if we look to our right, we see normal magnetic field. That normal magnetic field was being formed at the same time. Remember that as the molten material is coming up through this mid-ocean ridge here in the center, it is pushing the seafloor in both directions. So this normal seafloor, this normal magnetic field seafloor here in the center, that's all being formed at about the same time. Where would our youngest seafloor be? Hopefully you said right here at the center, at the mid-ocean ridge. Where would our oldest seafloor be? Hopefully you said out at the two edges. Both the left and the right side represent the oldest, because again, as this process is happening, the molten material is coming out through that center, through that mid-ocean ridge, and it's moving things out in both directions at the same time. So the reversed magnetic field that we see over here, and this reverse magnetic field that we see over here, those are were formed at the same time. That part of the seafloor used to be closer here towards the center, but as new seafloor was made, it was pushed towards the side and pushed toward the other side, sort of like conveyor belts that start here at the center and push their way out to the edges. If we move to the next normal section, this normal section and this normal section were formed at the same time as each other. Again, those used to be seafloor that was here at the center at the mid-ocean ridge, but they're older seafloor, so as the new seafloor has formed and pushed old seafloor to either side. And finally, our reversal over here and our reversal over here also occurred at the same time. That rock was formed at the same time. So if we were able to age or date those rocks, we would know that. Now let's take a minute to look at some of our questions. How many times has the magnetic field reversed itself in your model? Now it's important to remember, as we just discussed, that this portion of seafloor corresponds to this portion of seafloor. So this reversal is actually just one. It happened at the same time, right? Same for this normal and this normal over here. Those are part of the same event, part of the same time period. So those are going to be counted as one reversal, this together. Question number 5. If the last reversal of Earth's magnetic field occurred 750,000 years ago, and previous reversals occurred on average every 250,000 years, how old is the oldest rock in your model? So what that is saying is that the last reversal, so that's this one, that happened right here, and again, remember that's the same event, right? The same time period, because this is happening on both sides. It's symmetrical. Yeah? So this last reversal happened 750,000 years ago. So let's get our pen out and let's note that down. So this last time happened 750,000 years ago. Right? And then it tells us that previous reversals occurred on average every 250,000 years. So if this one occurred 750,000 years ago, and then this one occurred 250,000 years prior to that, and then this one occurred 250,000 years before that. If we know all of that information, then we should be able to figure out how old our oldest rock is, which is represented over here. Now we could also have very easily counted those same things, but over in the other direction, because again, these are symmetrical, they're happening at the same time. So we only needed to count in one direction, and that will give us the answer to how old the oldest rock is, and that is the same age here as it is over here. Question number 6. What type of plate boundary is represented by the mid-ocean ridge? Describe the movement at this type of boundary. We've talked a lot about that, so that one should be an easy one. And lastly, it's time to sum up all your knowledge and explain seafloor spreading.